Have you ever wondered what is going on when the car is going up a hill physics-wise? And why does it need more effort to go up a hill more than it needs when it's walking on a horizontal surface? And what type of affection is the hill itself applying on the car? And today, this is the questions we're going to answer. So to start us off, we're just going to discuss what is going on without including any numbers. So first of all, we're going to go when the car is moving on a horizontal surface. So we consider the y direction going up positive, and we consider the x direction going to the right positive. So right here, as we see, the car is steady. It's not steady, it's moving to the right. And if we look at the force free body diagram, we see how the normal force and the force of gravity is equal to each other. So if we go to the Newton's second law, we're going to find out that F net y will equal 0, because force of normal force will equal the force of gravity. But if we go to the F net x components, we're going to find out that the force of applied force plus the force of friction will equal the net force x. Then after this, now we're going to explain the system of the inclined surface, and we're going to answer the questions that we set. So first of all, we flip the compass a little bit, so it's parallel to the surface of the inclined surface, and we consider the force diagram. So the force diagram include the force of applied force, and the normal force, and the friction force, and the force of gravity force. But the only difference between this and the horizontal surface is that we divide the force of gravity into two components, where the force of gravity in the x direction resists the force of applied force, and the force of gravity in the y direction is opposite to the normal force. To prove what we just demonstrated, we use the Newton's second law, where F net y will equal the force of gravity in the y direction minus the normal force, which will equal 0. So the force of gravity in the y direction will equal normal force. And then if we go to the F net x, will equal the force of gravity in the and the x direction minus the force of friction plus the applied force And now we add numbers to the same thing we did right there, but with numbers. So we go right away to the Newton's second law. So if we assume that the car was 0.75 kilograms, and the applied force was 10 Newton, we'll try to find the normal force to find the friction, so we can do the F net x. So first of all, we find the force of gravity in the y direction, and we get the normal force, because F net y is equal to 0, because there's no acceleration, it's not moving up or down. So we get the net force equal to 4.9 newtons. Since normal force is equal to 4.9, we go to the kinetic force, to the force of friction and the kinetic force, and we will multiply it by the coefficient of kinetic friction, which we assumed that 0.1, that it's 0.1, and we multiply it by the net force, which gonna give us a 0.79. And by knowing this, now we can get the net for the F net x in the x direction. So F net x will equal the force of gravity in the x direction minus the friction plus the applied force, and we'll get a 0.31. It is 4.31. And now we successfully just answered every question that we included at the beginning.